Okay. Thank you very much for the opportunity to give you an overview of work that we're doing related to the volatile component on the moon, in particular water. In the backdrop here is an image where you can clearly see the water on the poles, and then in the equatorial region, it's pretty bland. And what we're going to talk about is how water might be formed and transported across the globe, the lunar surface. So the work was done by primarily Brant Jones. Okay, so a significant fraction of the information that's available for the superficial water comes from M-Cube. This was just brought up. There was an issue with this in the sense that they were only mapping the 2.8 micron band instead of the entire band. So the relative amount of hydroxyl versus water is sort of a question. But there was a very recent paper by our session chair, which I will talk about, which I think is a little bit more definitive with respect to the presence of molecular water. Okay, so this is a nice paper in GRL that came out very recently looking at the migrating molecular water from the LAMP measurements. And Amanda, if I misrepresent this, please correct me. There is some very clear, statistically significant signatures in the change in the spectral slopes in the vacuum ultraviolet region, which is correlated with the absorption of adsorbed water. And you can see this here. On the right-hand side, and in particular, the amount of water that is present on the highlands is more than what is present on the mare. And you can see this local variation. So the diminution or the drop near local time in noon is the stimulated removal or migration of water and a reduction in the absorption. Okay, so this conclusion was based on fitting this to a temperature profile, and it gave us roughly 1% of a monolayer with a greater than 1.2 EV binding energy. Now, the binding energy is the energy, the interaction of the molecule with the surface. So it's how strongly coupled the molecule is to the surface of the regolith. And a standard way of measuring this from the surface science community is a technique called temperature-programmed desorption. And I give you a little bit of an overview on this. A temperature-programmed desorption measurement is simply that. You have a sample in vacuum, and you control the heating rate very well, and you measure the number density of molecules as a function of that heating rate. And then you can extract out a desorption rate as a function of temperature, and then you can fit that data to this simple Polanyi-Wigner equation, which is shown up here. And the terms here is theta is the coverage, delta E is the number we're after, which is the desorption energy, T is temperature, N is the order of desorption, and what we extract is the rate of desorption. There are three main types of interactions. It's a physisorption interaction, which is the weakest interaction, and these are coming off at low temperature. There's a chemisorb state, which is the molecule is more strongly interacting with the surface. That's coming off as the second peak over here. And then if you move over to the right, there's a third peak there, and that's called dissociative chemisorption, where the molecule actually interacts with the surface and it breaks. And so water will stick to the surface as OH and H. And so you have the two fragments of water next to one another. When you heat it up, they find each other, they recombine, and they leave. Okay, that's important, and I'll talk about that. Because you don't see highly chemisorption states further down. The end of that curve is 400 degrees Kelvin. That's where 1.2 EV is going to be. So you don't actually typically see states of that type of binding energy. Okay, I didn't mean to go. Can I go back one here? Okay, so we built a system which is very specifically to do these measurements. We're in ultra-high vacuum. We have a liquid nitrogen cooled dewar that sort of is coming down from the top here and moves on and hits the sample head. And then we control the heating very accurately, and then we measure with a quadrupole that's right above that, the release. And then we can do this with a sample that's been designed so that we don't have to go through a background subtraction procedure, which is pretty important. Okay, so I have to go back in time when we first started this, and this was a collaboration with Darby Dyer and Carl Hibbets. And Darby gave us some samples, and she can tell you what K2294 means. It's her label. But it's a high iron glass to simulate the mare. Then we had JSC1A, a surrogate, and then Elbite, which Carl basically milled, and he gave us this sample. And so what you see is if I dose water onto the surface in a controlled way, This L means Langmuir. Langmuir is a sort of unit of dose that the surface scientists use. It's 1 layer per second covering 10 to the 15 sites per square centimeter. What you can see is for the glass, you've got this very boring thing here. This is ice, and it doesn't chemisorb anything. For the mare, you see some chemisorption, and for these albite samples, which are all ground up, there's more chemisorption. Well, what does this tell us? It says the more glassy the sample, the less it chemisorbs water. So this is important. The more glassy, the less water it'll take, okay? Now, here's some data that we recently took, and we finally submitted this. All right, so this is a TPD of a highland sample, 141.63 on the left, and a mare sample on the right. And the solid black line is the data. The pink line is the overall fit. And there are several things to note on here. First of all, the mare, the amount of signal coming out, so these are on the same axis, they're on the same scale. The amount of water on the mare is significantly lower than on the highland sample, and that's consistent with several other samples that we've looked at. And then there's 2 features here. There's this green thing, which is the low temperature feature, and then there's this blue thing, which is a high temperature feature. The green thing is the normal standard desorption event to the off of the surface and into the vacuum. The blue is more complicated because these are particles, so there's a desorption event followed by a sticking and then a reabsorption and being moved out. So there's a little bit of a diffusion component to that. And on top of that, there is this recombinant desorption step, right? So we can model this and fit this. The first approach is to do a simple sigmoidal fit to extract out the low temperature component, which we did, and when you do that, then you can use the standard Polanyi-Wigner equation to extract out the binding energies for those that are simply the desorption events that we know are going to the vacuum, right? And what you want to do, though, is pay attention to the fact that this binding energy, when you recast this, and Bruce Kay has a very nice paper on this, the binding energy is a function of the coverage. And this makes a lot of sense. If these fragments are next to one another and they have to meet each other, to make water, the closer they are, the less energy it takes to get them to do this. Further away, you have to add more energy into the system to get them to move around and meet each other. Okay, so we can do that, extract that, and what you get is the activation energy is a function of coverage. So this is the activation energy distribution. You can recast this into a site probability distribution as a function of coverage. You do this for both samples, right? And it turns out, not only does the mare not have as much water, but it turns out that the binding energy distribution is significantly narrower, right? So it has a narrow energy distribution, far less water. And so we're not exactly sure why this is, but this is our interpretation. And that is likely telling us that the mare has a larger agglutinate content and a glassy content, and it may be relevant to the amount of iron and titanium that is present in a strange way. It has to do with the fact that the surface, this is a surface phenomena, and the glassy surface is OH terminated completely. When water interacts with that, it's going to bind to OH and make ice. It does not chemisorb. It'll find OH and make ice, okay? And there's an anti-correlation actually with the maturity index, which I want to point out. Naively, you may think that the more space weathered the material is, the more water it takes up. This says the opposite. The more space weathered it is, the more glassy it is, then the less water it takes. Okay. So then we go back and we use these numbers and we fit the data again from LAMP. And we get exactly what Amanda got. It fits very well, right? Using this binding energy distribution. Now, there's a little bit of a difference, and we need to have 1 to 5% coverage for the highland, and then there's 0.8 to 1.2 coverage for the mare. But our fit is pretty good, right? But there is a twist, which I want to point out. So this works for the temperature programmed desorption, which is the thermal desorption component. But this is a VUV measurement. We're looking at a VUV photon interaction with the adsorbed water, and there's a state of water which she's exciting with this VUV photon, which actually stimulates the water to be removed, and it stimulates the water to dissociate. So in addition to thermal desorption, we have to consider what the VUV photon absorption event itself does. and that removes the water and dissociates it. So pictorially, what you have here in this blue is the ground state potential of water on a regolith. It absorbs a VUV photon. That absorption is a transition in water which is shifted a little bit, but it's a repulsive potential. So that's up here on the red. That repulsive potential leaves the water, makes the water leave the surface, and if it doesn't leave the surface, it breaks. So the VUV photon is changing the system as you make these measurements. So we need to know this. So we map this, and so what we've done is we've measured very carefully what the absolute cross-section is for VUV photon removal of the water. So what happens when the water absorbs this photon? And we do this by firing a laser right at the sample, and then a millimeter above the sample we fire another laser that is focused to a few micron spot size, and it's resonant with the transitions for ionizing water through particular rotational and vibrational states. And then we have a pulse laser, and a pulse, we have two pulse lasers, so you can vary the time between these and measure velocity resolved or quantum resolved velocity distribution. These ions then come up against the phosphorus screen, and we can also get an angular distribution, which is not relevant to this measurement. What is relevant is you get these velocity distributions, and you can sum up all of the velocity distributions in all the quantum states. You know your flux of the photons. You can get an absolute photo destruction or photo removal cross-section. And we've done that. Now, it turns out that the breccia, these were not exactly the same samples that we did the TPD measurements on. These are slabs. And we did a breccia and a basalt sample, and they're normalized to one another. Again, the amount coming off is not the same. The velocities aren't that high. You can get up to a couple thousand Kelvin for a small part of the distribution. They're on average about 550. You integrate these and you get your cross-section. So here's the standard absolute cross-section. It's big. It's 10 to the minus 18 square centimeters. And it's large at low coverage. So if I go to a low coverage, I have a very high removal rate of water from the VUV photon. So that's interesting, because if we go back and we use the known fluxes of photons and this cross-section, we get a removal rate of water, which is 40% of monolayer per diurnal cycle. So I believe that Amanda, and with Amanda's numbers and our numbers, what it says, it implies that because the PSD removal rate is so high, and she can see this in the measurement in LAMP, there has to be another source term which is greater than the removal rate. There has to be. And so what is that? And we will just put up a speculative one, which I think is possible, and that's the recombinant desorption step, which is these terminal sites can find each other and recombine and form water. And this is produced by this process called recombinant desorption. We've measured this on mare samples and highland samples. Again, the water from the highland is higher than the mare. But our results, when we compare them to the LAMP, says that there is probably much more water migrating around on grains nearly everywhere where T is greater than 200 Kelvin. So water is not just in the polar traps, but it's running around a lot. And with that, I'm going to be on time and leave three conclusions. That water in general doesn't like to stick to the regolith. It's roughly a binding energy of 0.6 eV, but there are some sites that go all the way out to 1.2. Those are the ones we need to fit the data that Amanda had. The LAMP data can be modeled very well with those, but if we pay attention to PSD, which is non-thermal desorption, we have a high cross-section. We therefore need another source term, and I would put forward that one of these source terms could in fact be recombinant desorption. And that I will end. On time. On time.
Okay, we have time for a question from Dana.
Go ahead, Bill. Okay, so you're looking at a couple different processes here, is that correct? Where some of the desorption products would be water, but also from this PSD, you would mainly have OH, is that true?
Okay.
Or,
So that's a good question. So I gave you the total removal cross-section. That includes the water and OH and H, right? We've measured the hydrogen branching and the water. And I don't have information on the OH, but they're all in there.
So is water significant?
Yes, water is a significant component. It's actually the primary component for the low coverage. So the water likes to leave at low coverage primarily as molecular water, and it is very vibrationally and rotationally excited. So yeah, and then that changes as I get to the higher coverage, and then they start to form ice. Then the water desorption competes with the dissociation.
Okay, thank you.
Yeah.
Really super quick?
You bet. So if there's all this water, why wasn't it seen in the Laddie? And
Yeah, I knew that was coming, Bill, and I
Yeah, I
thought
know.
I
That's-
actually
you knew I would ask it.
I absolutely thought that was what Dina's question was going to be. So I'm not really sure whether or not Laddie has the time resolution to see this, and also the water velocity distribution is around 550 Kelvin, so I'm not sure it gets there, but I don't know why they
that
don't see
temperature,
it.
it should have gotten up to the Laddie. Yeah. Okay, interesting.
Interesting, yes. Okay, super, super, super quick.
Well, you know this, Tom, but Casey Honeyball in Hawaii has found a 6-micron HOH bend molecular water signature at high latitudes in the poles, so it's complementing what Amanda's done.
Yeah, and I think that the numbers here will give you a relatively high concentration that is not what people expect. Pretty high concentration.
Okay, well, neat stuff. Thank you.